Okay, so just to sum up, we have this result that from Dirichlet theorem, actually, that if f is in L2, so let's say that we're considering minus pi periodic functions, but you know that we can extend that very easily to to functions defined only on a bounded interval. Then if I'm using some inner product in L2 that would be defined by 1 over 2 pi integral from negative pi 2 pi of f of x, I should take the complex conjugate of g of x if ever we have complex values times dx. Then I can express f as, well, that's an equality almost everywhere, of course, because you see that, you know that in particular for discontinuities, the function, the trigonometric series associated to the function is going to take the value that is the mean value between the values at the discontinuity of f. So I'm just using the same kind of things that we learned last year, that I've got a basis, I've got a vector space. Furthermore, it's an orthonormal basis. That's what we've just proved previously. So I can use this way of writing my function. It's going to be linear combinations of items of my basis, and the coefficients that come in front of them are given by the inner product between my function and the corresponding basis item. Okay, so times EINX. Okay, and so, oh, sorry. And so don't forget that then, of course, this coefficient here is computed as 1 over 2 pi integral from negative pi to plus pi of f of x. Conjugate of EINX is going to be given by E minus INX dx. Okay, so so that we really have something like f is equal to sum of on all integers of Cn EINX, and that's the value of the Cn. Okay, what do we know? Also, we know something about the norm of f. Okay, remember what we did about vector spaces with when you had an inner product with an orthonormal basis. That would just be an extension of the Pythagorean theorem. The norm is just going to be the sum of the coefficient squares of your linear combination. So that would just be the sum of Cn squared. Okay, for all n in Z. Okay, and that actually, ladies and gentlemen, this is what is called Parseval theorem. Okay, so let's have a look. It's written here. Okay, so in that last section of the lecture notes, you've got a quick summing up of actually the only formula you will have to use. So again, most of the time you will have those formulas reminded to you, but it's always as they are very, of course, logical, so you must have an idea what they look like. All right, so let's begin with so it's written for a function that belongs to L2 of negative t periodic functions. All right, so it's not only 2 pi periodic. You remember you have to do some kind of easy substitution in order to get that. So how do we define the coefficients? The coefficients are going to be given by 1 over 2t times the integral between negative t and t, f e minus in pi t over capital T. So that's just the substitution we needed. And then we can write that this being given, f is that infinite linear combinations of linear combination of the basis items, okay, with the coefficients given as before. And we have what I've just told you, the Parseval identity that tells you that the norm square of your function is given by the sum of the coefficient squares. You know that when you have this orthonormal basis, there's just an extension of the Pythagorean theorem. That means that also the norm square would just be given by this definition of the norm in L2 periodic functions. Okay, and then what do we have? Just below we have okay, the corresponding formulas reminded for functions for the trigonometric expansion. So if your function is only a real function, you can use an expansion as cosines and sines. If you have an even function or a function defined on a bounded interval that has been extended, periodized by even parity, you can use only cosines. If it's an odd parity, you can use only sines. All right. So this being said, this is the formulas that you have to use for the coefficients that come in front of the cosines and the sines. All right. So again, that would just be given by the scalar product, and so we're going to see a bit more precisely about this. But then that's just remark that this an stands also for the a0. Okay, we have an a0 over 2 because we wanted to get the same formula for the an, but whatever. We'll see where this over 2 comes from and why you don't have over 2 in the formula of the coefficients. Anyway, we have already dealt with those formulas for the coefficients an and bn. If that's how you define your coefficients, that's the expansion you're going to get for the function. And then again, we have the Parseval identity that tells you that the norm square of your function, so given by the same inner product as the one we've defined earlier, in that case is going to be given by this formula. Okay, pay attention to the fact that depending on how you've defined your coefficients, this formula will be slightly different, whether you have plugged a 2 or not in that definition. You will have slightly different values here. Okay, so these are given as consistent notations. All right, again, pay attention to the fact that if you're looking at some other sources, they may have some different way of normalizing things. Right, so let's have a quick look at well, what's the basis, the orthonormal basis we get for the cosines and sines. Okay, so what do we want? We've already seen that the functions, so let's say cosines of k pi x over t and the sinuses of well, let's take another p pi x over t. These ones, they would all be perpendicular with respect to the inner product. Well, we just proved that. We just said that if you take the integral on well, from negative t of these functions, you would get equal to 0. And if you use, and that's just calculations you can always do again. And if you use the cosine functions, it's going to be 0, or only, well, 2 cosines or 2 sines. It would be 0 if you have different indices, and well, different from 0 if you have the same indices. So what are we going to do? So we already have some orthogonal family. Okay, all the cosines and sines, right? So if you take the union of those two families, the cosines, so k, and the sine family. Okay, so we know that, so p in set of natural number, k in the set of natural number. This is an orthogonal family. what's left for us to make an orthonormal? One is we just have to normalize our coefficients, right? So let's take let us build our our family. So the first item of our family will obviously be 1, right? So that will be, let's say that we will put that E0, let's call E0 our family, our first item of the family. So let's see if we have a correct norm of 1 for this one. So if I take my inner product to be 1 over 2 times t equal between negative t and t of 1 square dt or dx, whatever, of course that's fine, that's going to be 1. So I can put, so the norm of E0 is indeed equal to 1. All right, now let's take a look at, let's put ek is equal to the cosine of k pi x over t. Then what do we have? What's the norm of this ek? So norm square of ek is going to be given by 1 over 2t times t cos square of k pi t over capital T dt. And if you compute that, that's something, so maybe pause and be sure you know how to do that. You're going to get 1 over 2. Okay, so that if I want to norm my function, I should put actually ek is equal to my cosine divided by its norm, so the norm being 1 over square root of 2, so I should multiply ek by square root of 2. Okay, so let me write that. Square root of 2 times the cosine. And similarly, I will build my family fk as being built out of the sinus of k pi x over t, and you will find that the norm is, well, the same. So you will have to norm that by multiplying by square root of 2. That means that if we define our function f, if we use Dirichlet theorem and say that f of x is equal almost everywhere to the sum of, well, we're going to have k in n of, well, we need in n star. Well, we have to differentiate. Okay. So we have the 0 element. So that, what would be the 0 element? That would be f with E0 times E0 plus, then I will have the sum in for k in n star of, we need the two families, ek and fk, so that's going to be f with ek and times ek plus f with fk times fk. All right, let's have a look at the first one. So we're going to give names to those coefficients because they are not exactly the same ones as the one we defined first, because we didn't use that square root of 2 normalization. All right, so what about that one? That's going to, let's say that's a0 with a hat, that's going to be ak, sorry, with a hat, also to differentiate it from the original one, and bk with a hat. All right, so what do we have then? What's the relation between a0 and a0 hat? A0 hat, okay, is given by then inner product. So that's 1 over 2 times t integral between negative t and t of my function f of x times so 1 dx, right? And a0 was actually given by the same formula, but without the 2. Okay, so obviously we're going to get a0 hat is going to be a0 over 2. Okay, and then what about the other ones? We have that a hat, the usual expansion of f should be given by ak cosine of k pi x over t plus bk sinus of k pi x over t. All right, so what is different is that we have normed our function, right? So what are we going to get? So let's see the relation we have between those coefficients. So for instance, the a hat k should be given by, so we have the square root of 2 times 1 over 2t times, so negative t of f of x times the cosine of k pi x over t dx. All right, so the square root of 2 in front of my integral comes from the normalization of the cosine. Okay, and then when I will multiply it again with here with the cosine, I will also multiply it by square root of 2. All right, so that you will have ak hat times my ek formula, so that's which contains the square root of 2 times the cosine of k pi x over t. And here you've got also the square root of 2 times square root of 2 over 2 times my original ak description. In the ak, you only had, you didn't have that part. Okay, without that part, that's really the formula we used for the ak. But if you see what we have here, we've got square root of 2 over 2, and we've got square root of 2 here. So that in the end, we really have that it's equal to ak times the cosine pi x, k pi x over t. So the definition we had, it's absolutely equivalent, right? But the only difference is that, well, if I'm now using this orthonormal basis description, that's how we should write the components in that basis of my function f, right? And you get the same thing for the bk. This being said, it's going to have to change slightly the formula we get for the Parseval identity. Okay, that means that my function f of x should be written almost everywhere as what we said. Well, a hat 0 times 1 plus the sum on k in n of n star, sorry, of a hat k ek plus b hat k fk. All right, so that if I'm using Parseval identity, that means that the norm square of f is just going to be, sorry, a hat the sum of a k square, a hat k square plus, well, I also need, sorry, all those. All right, b hat k square, and I also have to add the a hat 0 square. All right, so that's when using those coefficients that have been obtained from the normalized version in order to get an orthonormal basis. But now if I'm using, as you saw, it's completely equivalent. If I'm using my original coefficients, that's going to be slightly different. Instead of the a0 hat square, we said a0 is actually a0 over 2, so that's going to be a0 square over 4. And then we said that the relation between the a hat k a hat k is equal to 1 over square root of 2 of the ak. So what are we going to get? And same thing for the b hat k, it's 1 over square root of 2 times the bk coefficients. So what comes next when I'm doing my equality of norms? Sum of ak square over 2, so plus bk square over 2. Okay, so that's why in the formula you will have some some a0 square over 4 and 1 over 2 that's going to come as a factor in front of the squares. That's the formula that we have here. Okay, so you've got divided by 4 and divided by 2 for the rest of the thing. So you see where it's coming from. It's come from the normalization of our orthonormal basis made out of the cosine and the sines. Right, so this formula, so Parseval formula, is going to be very useful. Again, it depends on how your notations were given, right? But in the end, that should give you the same result. And we will use that also in order to compute some complicated integrals, right? Sometimes it's going to be simpler to compute the value of some infinite sum than some integral. So we'll see that in some examples.